an interactive application to analyze the existence of limit cycles using the describing function. This work describes the development of an interactive tool to illustrate the analysis of Lure systems through the use of the describing function. This is a classic tool that is usually presented in the introductory courses of nonlinear control systems present in the majority of master's degrees in control engineering. Control systems are each time more complex, and control engineers require more sophisticated tools to analyze them. The need to improve the performance of control systems and the implementation of state and parameter observers that use nonlinear models has led to the introduction of nonlinear systems theory in many engineering studies, and in particular in master's studies. Unfortunately, control theory for nonlinear systems is not simple and has a very important mathematical component that sometimes makes it difficult to assimilate by most students, especially in the allotted time for their courses. It is well known that interactivity can be a valuable pedagogical tool to introduce students to especially complex topics and, in particular, to automatic control subjects. For this reason, interactive tools have been developed that aim to facilitate the introduction to students of different areas such as control based on sliding mode, the study of dynamics in the phase plane, or the study of closed-loop systems through a describing function, among others. In recent times, there has been a very important boom in the use of computer tools and graphic and interactive tools in particular for teaching automatic control. A large set of applications have been developed for specific concepts, and complete courses have been designed based on these types of tools. By far, linear control systems have focused efforts on this type of development. However, nonlinear systems are beginning to receive increasing attention, and tools that illustrate techniques such as the phase plane or the describing function have already been developed. One type of systems that has received a lot of attention, both from a conceptual and practical point of view, are the Lure type systems. Also, they were one of the first nonlinear control systems that were studied in the framework of nonlinear systems control. Lure-type systems can be studied as the feedback connection of a linear system and a static nonlinear function. The Soviet engineer and mathematician Anatoly Isakovich Lure was one of the first to formalize this type of problem. The study of this class of systems is included in most introductory nonlinear control system courses and books, such as Applied Nonlinear Control by Slotin and Lee, or Nonlinear Systems by Khalil. Lure-type systems can offer very interesting dynamic behaviors, such as limit cycles, which can be studied using the describing function method. In addition, the study of this type of systems is usually connected to the absolute stability problem and the Popov and circle criteria. In particular, Lure-type systems' dynamics behaviors can be summarized as closed-loop instability, asymptotic convergence to an equilibrium point, or asymptotic convergence to a limit cycle. The characterization of limit cycles is usually not easy. A tool that allows an approximation of the same is the describing function. Describing function analysis assumes that it works with a Lure-type system and offers a heuristic methodology that allows an approximate characterization of the closed-loop steady-state behavior of Lure-type systems. It is a classical approach already developed and presented in the 1960s by authors such as Atherton or Gibson, but which continues to offer useful and interesting results, especially for engineering students. It is also a technique capable of handling non-linearities that present discontinuities or that are piecewise defined. The main hypothesis used to formulate the describing function is that the limit cycle can be explained in terms of a single harmonic component. Under the assumption that the limit cycle can be explained in terms of a single harmonic component, the output of the describing function, u, is assumed to be a periodic signal that can be written via its Fourier series, as shown. It is important to emphasize that Fourier series coefficients depend on the e-signal amplitude A. The output y can be computed using the frequency response of g of s and the value of u. As in steady state, the error must be equal to minus y, the output, we can then start to establish the conditions for the describing function. As said before, the main hypothesis to formulate the describing function is that the limit cycle can be explained in terms of a single harmonic component. Hence, both the input of the describing function u and the output y can be expressed as shown in red. As in steady state the error equals minus the output, we can obtain this expression, which relates the amplitude A, the transfer function of the linear block, and a complex number C1 that depends on the amplitude A. The existence analysis can then be graphically performed. To do so, we define an expression, n of A, understood as the generalized frequency response of the nonlinearity. df of A as minus 1 divided by n of A is the describing function. Usually, the evolution of df of A as a function of A is plotted over the polar plane jointly with g of j omega as shown in the figure. In case that the two curves intersect, a solution exists. The solution defines the limit cycle amplitude and frequency. Notice that more than one intersection might exist. Thus, more than one limit cycle might exist. As explained in the paper by Sridhar, a general method for deriving the describing functions for a certain class of nonlinearities, many nonlinearities can be characterized as piecewise functions. This figure shows the general model from which 9 nonlinearities without memory and 14 nonlinearities with memory can be derived. The bottom of the figure shows a sine wave input, and the right side of the figure shows the output waveform according to the nonlinear characteristic. Taking Sridhar's parametrization of the nonlinear characteristics as piecewise functions and their corresponding expression of the describing function, an interactive tool has been designed to illustrate the describing function analysis, which we present in this video. This interactive tool has been developed using Sysquig, as it is a very suitable environment and language for applications and interactivity. Example 1. Saturation. Saturation is one of the static nonlinearities that is present in all practical control systems. First, let us introduce the interface. The main window is composed of 4 plots. On the left side, at the top, we see the input sine wave in blue. We can adjust its amplitude by dragging the interactive point placed at the positive peak. We can see the value of the amplitude when we place the pointer of the mouse over that point. The value appears at the left bottom corner of the window. In purple, we can see the output waveform according to the nonlinearity defined on the plot below. On the nonlinearity plot, we see in fact now a saturation defined by the red points. The red points are interactive, whereas the black points will move accordingly to their symmetrical pair. On the right side of the window, we see at the top the plot of the describing function, in particular of its real part, as the nonlinearity plotted on the previous plot has no memory and thus the complex component of the describing function is null. As can be seen in the describing function plot, the gain of the nonlinearity first harmonic n of A is constant until the amplitude reaches the saturation level. Subsequently, the gain begins to decline. Therefore, the describing function starts at -1 divided by k for amplitude 0, where k is the saturation slope, and tends to infinity on the negative real semi-axis as the amplitude tends to infinity. In this example, the slope k is 4 divided by 3. On this plot, we can find another interactive element, which is the dotted line, which also shows the amplitude of the input wave. As we drag it, the amplitude of the blue wave on the input-output plot varies as well. Finally, on the right bottom corner, we find the polar plot, in which we can see the curve of the linear component of the system in black and the describing function in green. As it can be seen, no intersection between df of A and g of g omega exists. This indicates that no limit cycle exists. Additionally, as g of s contains no poles in the left-hand side complex plane and there is no encirclement of df of A by g of j omega, means that the closed-loop system will be stable and will converge to an equilibrium case. We can set the transfer function of the linear element on the Settings tab. In this pop-up window, we can write the coefficients of the numerator and denominator of the desired linear transfer function. In this case, the transfer function is 10 by s plus 10 divided by s plus 1 by s plus 100. Now let us modify the transfer function and change it to minus 10s divided by s to the square plus 2.1s plus 100. We first get a warning, as the polynomial for the denominator contains complex numbers, and then we see the Nyquist plot corresponding to the new transfer function. In this example, there is an intersection between the describing function and the frequency response curve. This intersection occurs at the point minus 4.8 plus j0, which corresponds to omega equal to 10 and A equal to 24.1, as we can see in the legend, but also at the left bottom corner of the window when we place the pointer over the intersection point marked with a cross. Example 2. Dead zone. The dead zone is another of the usual nonlinearities in many control systems. It presents a null gain for amplitudes lower than the clearance of the dead zone and subsequently begins to grow with a certain slope k. This means that the describing function is close to minus infinite for small values of the amplitude and tends to minus 1 divided by k as the amplitude increases. As it can be seen, no intersection between df of A and g of j omega exists. This indicates that no limit cycle exists. We have presented an interactive tool that is currently being developed in order to illustrate the describing function technique. This interactive tool aims to facilitate the study and learning of the describing function in a visual and engaging way as a tool for the study of nonlinear Luret type systems. We are currently working on integrating methods to obtain the exact solution, as well as integrating other elements for further and deeper study and understanding, such as the circle criterion or the Popov criterion.